अस्सलाम वालेकुम।
वालेकुम अस्सलाम अब्दुल मालिक, हाउ आर यू?
सर ठीक है, आप सुनाए सर।
मालिक, हाउ इज एवरीथिंग?
सर ठीक सर, वो मैंने अपने प्रोजेक्ट को इम्प्लीमेंट भी किया था, स्टार्ट किया था मैंने, वो मॉडल भी बनाया है। वो मैंने बनाया CNN पे। ठीक है सर। और उसको मैंने इमेजेस ट्रेन भी कराई है, जो मैंने डेटा सेट मेंशन किया था, तो वो एक्यूरेसी मैंने अभी कंप्यूट की थी, तो वो 78% आ रही है। अब मैं सोच रहा हूँ ट्रांसफर लर्निंग के थ्रू करके देखूं।
थोड़ा थोड़ा
जो मैंने
बैकग्राउंड
अभी
प्रोजेक्ट का, व्हाट वाज द बैकग्राउंड?
सर यही ड्राउजीनेस डिटेक्शन यूजिंग इमेज प्रोसेसिंग, डीप लर्निंग
व्हाट
CNN।
डिटेक्शन?
ड्राउजीनेस सर, ड्राउजीनेस।
ओके, ड्राउजीनेस। सो यू हैव डेटा सेट है?
जी सर, वो डेटा सेट मैंने नेट पे सर्च किया तो एक वेबसाइट है,
हाँ हाँ,
उसमें अच्छी खासी इमेजेस थी आईज की ना,
सही।
तो मैंने उसी को यूज किया है।
ओके ओके, सो हाउ मेनी इमेजेस आर देयर फॉर ट्रेनिंग द मॉडल?
सर कम 10,000 से ऊपर ऊपर है।
Okay, and those are people who are feeling drowsiness, है?
सर असल में मैंने डेटा सेट लिया सीधा आई का, कि आई क्लोज है कि नहीं है। तो
सही।
वहाँ पे जो डेटा सेट पड़ा है ना, उसमें ये है कि 39 डिफरेंट पीपल्स के सिनारियोज हैं। जैसे हम इमेजिनेशन नहीं करते, सॉरी डेटा आर्गुमेंटेशन नहीं करते, उसके थ्रू उसने इमेजेस जनरेट की हुई हैं। और
सही।
उसने ये भी है कि उसमें जो ग्लासेस वाले बंदे हैं उनकी भी इमेजेस हैं, जिसकी
हम्म,
वजह से मुझे वो डेटा सेट फायदा दे रहा था।
अच्छा अच्छा, सही
अगर
सही।
मैं ग्लासेस पहन के भी आंखें मीन्स जब कर रहा हूँ ना, बंद कर रहा हूँ, तो
हम्म,
फिर वो काम करेंगी। इसीलिए मैंने वो डेटा सेट इसीलिए चॉइस किया।
गुड यार, वेरी गुड वेरी गुड। सो यू आर सेइंग कि 78% एक्यूरेसी दे रहा है। असल में वो ट्रांसफर लर्निंग वाला मुझे नहीं, आई एम नॉट वेरी मच कॉन्फिडेंट कि वो अच्छा परफॉर्म करेगा, क्योंकि इन ट्रांसफर लर्निंग आई डू नॉट थिंक वी हैव इमेजेस फॉर ओपन आईज एंड क्लोज आईज।
सर देखते हैं, कोशिश करते हैं। मैंने उसमें लिखा है कि मैं उस पर भी चेक कर लूंगा, तो नेक्स्ट वीक में मेरा यही प्लान है कि दोनों की मॉडल की एक्यूरेसी कंपेयर करना, और फिर मैंने उसको टेस्ट करना है।
चले चले,
फिर मैंने
अच्छी अच्छी बात है, अच्छी बात है। लेट्स सी लेट्स सी। Okay, so we are joined by only 1, 2, 3, 4, 5 people. Where are others?
मैसेज करता हूँ, मैं देखता हूँ, ग्रुप में मैसेज कर देता हूँ।
ग्रुप पे मैंने मैसेज कर लिया है, तो why these guys are not joining?
सर एक मिनट वेट करो, 12 बजे टाइम हो शायद नहीं करे।
12 थी यार, मतलब मुहूर्त 12 थी यार, ताऊ जो वाल कला कला पोया यार। मतलब तांजो
सारा साउंड भी थी यार
11 11:59 था
अनन
सर
माना
कुछ
12
क्लासेस
कम ऑन
12
एग्जैक्ट 12 थी
12:30 पे होती
हिक ब मिनट वेट करियूं था सुभान ता ॿुधायो हाउ इज योर प्रोजेक्ट गोइंग ऑन
सर असां डेटा सेट वगैरह एक्सप्लोर कयूं पिया तव्हांखे मोकिलियो हुयो आइडिया वगैरह
कहिड़ो डेटा सेट जे ते कम पिया करे
क्रेडिट कार्ड फ्रॉड डिटेक्शन ते कम कयूं पिया
क्रेडिट कार्ड फ्रॉड डिटेक्शन ठीक है ऐं मतलब सुभान तव्हां प्रोजेक्ट जमा त न करायो आहे तव्हां सबमिट त न कयो आहे
न सर असां सिर्फ़ हू कयो आहे इहो जेको आहे न आइडिया वगैरह सबमिट कयो आरिफ जी आइडिया सां कयो न सर
न काफ़ी सारा स्टूडेंट्स आहिनि जिन सबमिशन ही कान कई आहे ऑनलाइन आई सी ओनली 8 groups have done the submission and
there
and
are total
Subhan, have you guys submitted? I mean, has your group submitted?
यस सर आरिफ जी आइडिया सां कयो आहे आरिफ
Okay, Arif Jaidi sa. Okay. Uh, okay, project idea submission. So there have been only, okay, now 11 submission. Okay, some of them might have submitted late, 26 minutes late, 1 minute late, 2 days late. नूर ये क्या है
अस्सलाम वालेकुम सर सर
क्या सर
लेट हो गए थे सर
नहीं क्या लेट हो गए बात सीधी है मैं कंसीडर ही नहीं करूंगा जिन्होंने लेट सबमिशन किए 19 आवर्स सर्वन 5 days श्याम कुमार श्याम आर यू देयर
Sir, I think only I have submitted on time.
क्या कह रहे हैं
Sir, I think only I have submitted on time. All others are late.
अब्दुल
पहला
मालिक
नाम पढ़ लो
Abdul
Abdul
Malik,
Malik bhi hai.
Arif, these guys have submitted on time. And those who have submitted late, I will not be considering. I mean, this is not joke. This is not,
सर सर कुछ आवर्स ही जो है ना सर लेट हुए थे क्योंकि वो इंटरनेट के इश्यूज थे और वीडियोस के काफी रीटेक लेने पड़े थे वो पावर पॉइंट का कोई इशू आ रहा था उसको रीइंस्टॉल किया था पूरी ऑफिस को
या देखिए ना मैंने आपको ना कोई आज नहीं कहा था ये कल सबमिशन डेडलाइन है मैंने आपको
एग्जैक्टली सर पर
on the very first day of the course I informed
जी
you
सर वो मैं नहीं कह रहा कि
and then I gave you I think couple of weeks time कि ये rubric है ये project का idea है तो ये अनफेयर है यार ये अनफेयर है ये मतलब मास्टर के साथ जुल्म है अगर आप इस तरह से लेट करोगे ना मतलब you are actually kind of causing my demotivation 5 days late anyway
sir my
11 group have submitted let's see so we are now going to formally start our class we waited for 10 extra minutes I hope all of you can see my screen
yes sir
okay so today we have yet another very exciting class this is about
तव्हां थोड़ा यो सॉरी टू इंटरप्ट सर आइडियाज तव्हां ॾिठा आहिनि सर थोड़ा असां हुन ते कम करण स्टार्ट कयूं
तव्हां बिल्कुल कम करण स्टार्ट करियो some of the ideas have already evaluated and some of the ideas I'm still figuring out when to have 2 hours time availability at my end I will review but you can straight away start working on your projects because many of you have been discussing with me individually some of you have been in touch with me on WhatsApp others have even come to my office so most of your ideas I completely agree with you so you can start work on those
okay sir thank you
okay so in previous class if you remember we started working with the text data I'm just recapping what we learned in last couple of weeks so that we can make sense of content which we are going to learn today again to be very honest with you these are the contents which are highly exciting you should all be understanding each and every bit of it because if you then these contents will assist you not only in your project but also after your degree so when we start working with text data, you know that we have to segment it into words and transform each word in vector. And we do it because we know that our neural network cannot understand text. It needs numbers, right? So the first step, in order that our text be understood by the neural network, we need to first convert text into words and then convert each word into vector. We discussed about word to vector, that is very sparse, right? And then we said word to vector, yes, it's very good on paper, but when we want to apply it in practice, you know, that requires a lot of memory, and that's not a very good option. So we said that we needed more, you know, vectorization methods which do not have a sparse dimension. It should have just maybe some fraction numbers, just one number to represent one word. Because in one hot encoding, if you have got 10,000 unique words, then the size of each word is 10,000, which we said practically it does not make a lot of sense. So that is the reason why we said we need alternate techniques. And in those alternate techniques, we saw that we can learn word embedding from our data. And then for that, we just need an embedding layer in our neural network. When we have got an embedding layer in neural network, it will automatically, you know, convert each word into vector. You know, the learning process then becomes same as we have in ordinary neural network. In neural network, we say that initially we will randomly assign weights, right? And then, you know, start the learning process. The weights will be updating at each iteration. We see the error and then we update the weight. So we say here in embedding layer, we will again have some random, you know, number assignment for our each word, and then we see the error. If error value is quite high, we do back propagation. We do not only update weights for the hidden layer of neural network, but we also update weights of the embedding layer. So we initially assign random vector to each word, and then as we move along the process of back propagation, we actually update not only weights of the hidden layer, but also you know, vectors of the vectorization process of the embedding layer, right? So we saw this works brilliantly, and we also discussed that usually this is a preferred option when you have got a lot of data. Say for example, if you have maybe 1 million instances, maybe 1 million text instances, there we say uh, let's learn embedding from the data. The advantage is, I mean, in your domain, your words might have different meaning than the words in general world, right? So there, when you've got a lot of data, the preferred option is to learn embedding from your own data. But if you've got a very small data set, maybe just 1,000 instances, 5,000 instances, 10,000 instances, then your data may not be giving, you know, a good relationship among the words. So the embedding there might not be very good. So we say that in that case, we will actually in that case, we will be using some pre-trained embedding. And pre-trained embedding, we discussed that we have GLOVE, which is you know, proposed by some Stanford guys. It was learned on Wikipedia as well as Common Crawl. And then there is also you know, not only word to vec, but there is also fast text from Facebook. There is word to vec. There are many, you know, embedding technique. And recent, the one which have actually brought a lot of revolution in the NLP era, it is actually BERT. BERT is based on the transformer. So, you know, a lot of embedding techniques are there. Some of them are pre-trained, other we can learn from our own data. But whole idea is you need to convert words into vector, words into numbers. The reason is simple. Your neural network cannot understand you know, text itself. The way we converted image into intensity matrix, we need to convert word into vector, right? Then segment text into character and transform each character into vector. This is, you know, alternate possibility. Depends on whether you work on word level or you work on character level. And then we say we can extract n-gram of words or character and transform each n-gram in a vector. Another possibility, I mean, if you want to capture a window of the sentence, then you can do that. So usually, I mean, token, just one word or one character, depending on what you are playing with, whether you are playing with the, uh, words or you are playing with characters. And then you do tokenization, you do vectorization. One-hot encoding is one such example. We saw these examples. This was, uh, 2 gram and 3 gram. We saw these examples in previous classes. One-hot encoding we have already discussed. We did it manually by using code, and then we also have some beautiful statements in Keras which help us create one-hot encoding from our text. Right? We discussed this. I mean, usually when you are playing with the one-hot encoding, they are binary, one and zero. They are sparse, very high dimensional, right? So we do not usually go for that option. When you go for word embedding, they are low dimensional, usually floating point numbers, and they are learned from data, right? So when you are using word embedding, two possibilities: use pre-trained word embedding, uh, or you learn word embedding from the data. These two possibilities I've already discussed with you. When you're learning word embedding with the embedding layer, if you have got small data set, I mean, you won't be able to create this type of, a structure in your words. For example, dog, cat, tiger, wolf, because all of them are animals, so they should be closely aligned. But if, say, for example, you've got a bird here, say, for example, parrot, then it should be somewhere here, very far away from all these animals. But these type of geometric relationships between words may not be able to be reflected if your data set is small. But if your data set is too long, for example, for fast text, they use all the text that is available on social media. That is a lot of text, and because that is a lot of text, so they were able to create these type of beautiful relationship. And the relationship, like if you subtract male from king and add female in that, it should result in queen, right? I mean, you see here, very interesting example. See here, they actually said they actually said they actually said uh, the queen equal to king minus men plus women, right? Men plus women. See here, so they say if you have learned word embedding on lot of text, then even these type of relationships you can maintain. Now what does it mean? It means that the embedding of queen, for example, the embedding of queen is, say for example, after learning from neural network, we came to know the embedding for queen is, say for example, 56. So they say the embedding for queen will actually be equal to this expression. And see how interesting this expression is. If you just extract man from king and you add woman in that, it will be a queen. So probably they might say that, say for example, point 90. Say for example, just a hypothetical assignment of vectors to the word. So say for example, king was given 0.90 and we subtract main. Say for example, it is 0.02. So that becomes maybe I say 0.5. Say for example, 0.5. And say for example, the vector for woman is 0.14. So these type of relationship will exist. So 0.90 minus 0.5 becomes 0.4, and when you add 0.14, that becomes 0.16. That becomes actually 0.56, which is actually embedding for the queen. So they say if you learn word embedding from a lot of data, these type of relationships will be possible. These type of relationships will be possible. I mean, for example, if I say maybe auntie, huh? Auntie. So auntie will be equal to aunt minus main plus woman. So they say that the embedding that you will be learning for this word will actually be equal to this word, because in real world these relationships are true. So if these type of relationships can exist in our word embedding, we can say, wow, that word embedding is really a good reflection of what the data is. And believe me, these type of relationships existed when we learned word to vector from Wikipedia, when we had glove from a common crawl and Wikipedia, that these relationships were existed, though it may not be exactly equal, but very close relationships. So any good word embedding should have these type of relationships. If you are able to make these type of relationships, if you are plotting things which are similar to each other, and if they are plotted very close to each other, congratulations, your word embedding is making a lot of sense. But if that is not true, I mean, if you are plotting, say for example, a girl with a lady, and if they are plotted opposite to each other, we know that in the real world, a girl and lady, they are not opposite to each other. So if you say, for example, say that for a girl you have embedding 0.9, and for a lady the embedding is 0.09, you say no, that does not make sense, because mathematically 0.9 is opposite to 0.09. Now, if girl is given 0.9 and lady is given minus 0.9, we say that does not make sense. So, any good word embedding should actually capture these type of real world scenarios. If that happens, then your word embedding is reflecting truly what is in your data. But if these relationships are not being maintained, then, we need to do something else. Right. So I hope you understand the concept of word embedding. Eh? Any question? Raise hand if you have any question. Just raise hand. Any question? If you have, you can ask question. Just raise hand if you have any question.
सर ये जो अभी आपने कॉन्सेप्ट बताया कि मतलब लेडी और गर्ल की जो वर्ड एम्बेडिंग वैल्यू है वो नेगेटिव नहीं हो सकती, तो क्या गर्ल और बाय की हो सकती है?
Excellent, super excellent. Thank you, Subha, for this question. I mean, if you say that for girl the embedding is 0.9, and for boy, if you calculated embedding minus 0.9, wow! I mean, because we know that girl is opposite to boy, which means that if you are getting a number for girl and if an opposite number for boy, then that word embedding is good. Say for example, for the word good, you learn 0.45, right? And for word bad, if you learn minus 0.5, wow! I mean, these are the relationships which are existing in the real world. These are the opposite word to each other, and if you are learning opposite number for them, excellent. And believe me, if you have got a lot of data, these words will be eventually learned. I'm not saying that they will be exactly opposite to each other. Maybe this is 0.45, this is minus 0.5. The difference is only minus 0.05, and that difference is a very minute difference. So the overall idea is, when you're learning word embedding, if these type of relationships are existing, your word embedding is really a good reflection of your real-time data. Right, so you're right. I mean, for boy and for girl, if the numbers are opposite, wow. But if the numbers are very same, we must say, oh, no, that does not make sense. Right. So the whole idea is we need to learn word embedding. It means we need to learn, some fractional number which can represent our words. And then rather than sending those actual words to the neural network, because network cannot understand word, we actually send those numbers. Right. Okay, so we have already seen this example. We added an embedding layer. We saw that this embedding layer acts like a dictionary. it takes word as the input and it gives us corresponding vector. We have already seen this example in our previous class. You know, we have also seen how to use pre-trained word embedding. Huh? Giller word to vector, we have already seen this in our previous class. I'm not sure how many of you have done these exercises. Raise hand those who say that, Dr. Shea, we have done this.
Sir, I have done some of this in pre-trained embedded layer. There are last three I have done. I have not done. I have done trained network on 12,000 positive and negative reviews, sir.
Okay. Okay. Shakil, how about you? Shakil, I think you raised hand, huh?
सर मां भी प्रीटेंड थे कम कहवा था प्रीटेंड लेयर थे.
Okay, okay. You have done work on pre-trained layer, but okay, but you know what was my question? Increasing maximum feature, because previously you saw that we were using limited word size. I think in that case we were using only 20. So we said you increase and see what is the impact. The common sense says it will improve the performance. Increase review
Yes,
size
sir.
to
It will
500,
increase.
the exact value. My common sense says performance should improve. Increase review word size and see the impact. This is in pre-trained. This was without pre-trained. Now this is in pre-trained. And we say increase training size to 10,000 because we were training on 200 instances. On 200 instances, we checked what is happening. And now I said, when you go back home, you should be doing these experiments. I never asked you to submit these, but if you just perform all these experiments, you will be developing a lot of your understanding. So I strongly recommend to those who have not still completed all these, they should do it. Okay, now, can you tell me what should be the word?
Yes, sir.
Word after drink. What should be the
Water.
word
Water.
after drink? Water.
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 Alcohol,
Cold
sir.
drink. Cold drink, water. There are a lot of words, sir. Yes, and sequence matter.
Exactly. Exactly. I mean, when I'm saying
Sir, wine.
वाइन भी हो सकता है सर.
who said wine?
Matter, sir.
Huh?
My sir.
सर मी सर.
तो जो है दिमाग खराब खबर दे. Okay. So after drink, I mean, all of you have come up with different, answers. From water to drink to wine. So obviously, you don't know what should be the word after drink unless you know the context. Now, Shazib, what should be the word after drink now?
सर
Milk, sir.
Huh? You cannot say now wine because cat, if she takes wine, yeah, she will become Shazib. So obviously, we cannot say here wine. Now,
समीरन जी के टू द वाइन पी सके सर.
yeah. So when context is clear, we know that the word here should be milk. It means that up to this point, we have been processing text without considering the context. Right? See here. What should be the character after P? What should be Iman?
PP.
Iman, what do you think? What should be the character after P?
सर पी के बाद
I'm
ई भी हो सकता है.
I'm not saying in alphabet. Do not say Q. So what should be after P?
सर अल्फाबेट या पूरा एग्जैक्टली मेरा क्वेश्चन समझ नहीं आ रहा.
Not in alphabet order. Not in alphabet order. My question is, what do you think in
Yes, sir.
English literature? What the character should come after P?
Sir, I guess E for pen. PE.
Why PE?
So usually pen अक्सर यूज होता है most of the time.
Okay.
आई लगा दे आई बन
अच्छा,
जाएगा.
आप कह रहे हैं कि पेन, आप कह रहे हैं E आना चाहिए, कह रहे हैं कि E आना चाहिए क्योंकि यूजुअली वी यूज पेन. अच्छा, मैं कह रहा हूँ कि यार जो डोमेन मेरा है ना वो एजुकेशनल नहीं है. द डोमेन दैट आई एम टॉकिंग अबाउट इज एक्चुअली मूवीज. ठीक है, अब मूवीज में आपका पेन कहाँ जाएगा? अच्छा, अब यहाँ देखें, व्हाट डू यू थिंक व्हाट शुड कम आफ्टर पी? थोड़ा मैंने कॉन्टेक्स्ट क्लियर किया हुआ है. मतलब P से पहले A, अब क्या आना चाहिए?
तो फिर बाद में फिर A,
है ना?
apart, APART.
I mean, there are many possibilities, but we have at least reduced the window size. I mean, we have reduced the possibilities.
Apple.
It can be Apple, so you can say that after P, there should be another P, because we are probably talking about Apple, right? So the thing is, Murtada, you can ask question.
सर ये नंबर ऑफ डैशेस मैटर करेंगे हमारे प्रेडिक्शन पे?
नंबर ऑफ डैशेस भी तो मैटर करते
Yes,
हैं।
obviously. These will also matter. The whole thing is, you don't know what should be next word or next character unless the context is clear. If I give you this context, say for example, APPL, and now if I ask you, all of you with one voice will say, sir, E, because the whole context is clear, right? So if I say, yes, if I say,
sir,
I'm in love with my, I'm in love with my country, which is, all of you will very unanimously say, what should be next word, right? I mean,
India, sir.
Who's hearing me?
Okay,
so we all say Pakistan, we all say Pakistan, because the context is clear. If I just say, if I remove this whole text and then I say what should come after is, I mean, you say, come on, give us background. What is before is? When I say before is, I have this sentence, then you say, yay, there should be Pakistan. Right. So the thing is, when you are doing next word prediction or next character prediction, you know that sequence matters. And this is exactly what RNN says. RNN says you have to consider the context when you're processing languages. Right. Even sequence matters. What do you think? What is this sentence? Working love, learning, we on deep. I mean, this is not a meaningful sentence. If you only change
we love
sequence of,
working on deep learning.
if you only change sequence of these words, you know, this becomes a very meaningful sentence. We love working on deep learning. So you know that even sequence matters, not only the context but also the sequence. So this is what RNN exploits. This is what RNN says, that I will use this information to improve, you know, many tasks of NLP. Some of those tasks are, you know, sentiment analysis. I mean, RNN or LSTM or GRU, they are very good at, you know, doing sentiment analysis. I mean, if you give them sentence, I really like the color of my new phone, you know, it's positive sentence. And if you say, I don't know by the camera of my phone, it's a negative sentence. You know, RNN or LSTM, by considering these sequences, they can predict label of the sentiment, be it positive or negative. And we call it sentiment classification. In image captioning, I mean, another very strong area where RNN and LSTM, these guys have contributed immensely. It is to generate captions for the image. I mean, look at this image. A person riding a motorcycle on a dirt road. Believe me, this caption is generated by a machine. This caption is not generated by human. Rather, this caption for the image has been generated by the machine. And machine has been able to generate because it understands the contents in the image. I mean, it knows that how mud looks like. It knows that how motorcycle looks like. It knows that how, you know, a person looks like. So all these information, when we train our network properly, especially your convolutional neural network, and if you train how to generate label, then even for those images which it has not seen in the past during the training, it can generate very meaningful captions. And if you are able to generate these type of meaningful captions, I mean, a lot of practical applications. For example, video copy detection is one good area where if you can understand image contents, you can do the, you know, video copy detection. Or if, say for example, you want to figure out if a theft event is happening, if someone is actually trying to steal a car, if someone is actually trying to steal a mobile phone or a bicycle. You know, if you can understand contents from image, if you can caption it, then you know you can apply it in many practical applications. For example, a guy having uh, a jacket bomb inside that he might blast. So if you are able to understand these type of contents, you can automatically give message of the warning to the law enforcement agencies. You know, if you only can understand contents of the image, and if you can predict these type of caption for the image, a lot of practical applications are there, and you can see how accurate these all how accurate all these captions are. Two dogs play in the grass. Huh? Two hockey players are fighting over the puck. A group of young people playing a game in Frisbee. So you can see all these titles which have been generated, all these captions which have been generated, they are very accurate. And LSTM is very good at these things. Right. Language translation, another very, very strong area where RNN and LSTM have contributed. I mean, you give them a French paragraph, it can give you English or vice versa. Here in this case, you can see we gave them English and it gave us French. This is called a sequence to sequence modeling. You can call it sequence to sequence modeling, or you can call it sequence to sequence translation, where we actually give one sequence, maybe text in one language, and it can give you an alternate sequence, translated version in other sequence. In NLP, we actually call it sequence to sequence, right? Sequence to sequence modeling or language translation, whatever you want to call it. But you know, all these are the practical applications of recurrent neural network. Okay, now let us understand. Let's understand what is recurrent neural network.
सर
Yes.
सर टेक्स्ट जनरेशन की बात, तो हम नेक्स्ट वन कैरेक्टर की बात कर रहे हैं ना? अच्छे हमने एग्जांपल देखी तो पाकिस्तान इज ए मतलब एक बहुत बड़ा वर्ड है. इस लिमिट को कैसे डिफाइन करेंगे कि ये कितने कैरेक्टर्स का होना चाहिए नेक्स्ट वर्ड विंडो साइज से सर?
No, I mean you usually do not define limit, because if you define limit, then you are actually limiting the capacity of your model. It is actually that you train the model and let the model decide what should be next word or next character, and let the model learn the size of sentences or size of word from the data. I mean, अगर आप उसको कह रहे हैं कि for example you say कि always generate a sentence of 10 words, then you're actually limiting your model. You should not do that. What you should be doing, you should ask model to learn, you know, what is the good size of sentence or what is the good size of a word. For example, if you are asking your model to generate next tweet, the tweet that you want to post today, you are asking the model to generate tweet. Now, if you train model on probably 10 million tweets, model will automatically learn that the maximum size for a tweet is 280 characters. And minimum size is just one character, right? So let the model learn from that. If you ask him to always generate a tweet of 10 words, model's capacity or its capability will be very limited, and we do not want to limit it. So we'll let the model learn it, because sometimes we tweet a lengthy tweet, 280 characters max, right? And sometimes we just write a couple of characters and they make a lot of sense. So you know that this size of the word or size of the sentence, we usually leave it on model, right? Okay, now let us understand what is RNN. So suppose the next word prediction. Here is what MLP would look like. We will have input, we will have hidden layer, and we will have output. You say, come on, this is exactly what our dense neural network is. We have input, we have hidden layer, and we have output. I mean, this is what we learned in first class, and you are saying this is RNN. Huh? There is a difference. This hidden layer actually receives input. You can see this was not possible in a sequential model in our fully connected dense neural network. There we had input layer and the input was being supplied only at the input layer. But here we say that input is not only being supplied at the input layer, but we are also supplying, input at the hidden layer. Now this input at the hidden layer is not the input which is the next word, it is rather what model has seen previously. So maybe now when you say, say for example, I say I have this input is, so I'm passing is from here, right? But here I'm passing what I saw before is, right? So before is my country, right? So maybe these are the two more words that I'm supplying to the model. So I might supply my from here, country from here, and is from here. Now I'm asking my model what should be next word. If I only give is, model says I don't know what you want to predict. But if I say before is, I saw my country. Now tell me, when I saw my country is, what should be output? Model will very confidently say it should be Pakistan, because it's about, say for example, Dr. Sheikh. Now, if I have written my whole, story since my childhood, I must have discussed somewhere what is my birth country, right? So model must have learned where I belong to. So now if I'm asking that in this story, can you RNN write one sentence? And these are the 2 to 3 initial words. Tell us what should be the fourth word. Model should be able to predict it, right? Believe me, all these latest inventions like chatbot. Chatbots are very big things these days. Usually, when you cannot answer questions manually, you actually design a chatbot, and these chatbot usually learn from the text available on your website. For example, I'm in Sakar IBA, we have a very big problem that people usually complain that when they dial on our admission office or maybe to our STS or to our QEC, people do not pick phone. I mean, they do not answer our queries. Or when they write on our Facebook, again, they might complain that our queries are unanswered. There, if we can have an automated chat box, because usually the question that people are asking, the answers are available on website, but they do not want to explore our website. For example, usual question might be when next OGDC and TFP will be announced. What is the last date of applying for admission in MS program of Sakara IBA? How many faculty members are having PhD at Sakara IBA University? Does Sakara IBA University offer computer science master program? I mean, all these questions are already answered on our website. I mean, usually people do not bother to explore the whole website just to get answer of their question. They just post a question on Facebook or maybe some query area where we can receive queries. So if you can train your RNN on complete text of Sakara IBA website, believe me, the chatbot should be able to produce answer for the questions which has been updated on our social media or maybe on our chatbot. So this is a typical sequence to sequence translation. When I say sequence to sequence translation, it is not only translation from English to Urdu, but it is also translation from query to answer. So one sequence is what is last date of applying for OGDC NTHP. Now this is the sequence. For chatbot, its answer is the last date for applying in OGDC NTHP is September 10. Say for example, now this data September 10, it must have learned from our website text. So you're doing nothing. You're just training your model on all the text which is available on any particular website, and then you are generating these type of sequences from that text and their corresponding sequences from that text. And if you are able to do that, you don't need to hire a guy who's all the time sitting on your social media answering these queries. I mean, maybe Sakar IBA might receive maybe 100 queries a day, which humanly, maybe it is possible that one guy can answer if you can spare a dedicated resource. But a company like Apple, they might receive millions of queries a day. And when they are receiving millions of queries a day, oh my God, you cannot answer them manually. You need some automated process. And that's where your chatbots are coming. And chatbots are nothing, they're just sequence to sequence translation. And RNN and LSTM, they are very good at, sequence to sequence translation. This is one big area that you might, yes?
सर इसमें मॉडल को फिर डेली अपडेट करेंगे, मतलब जो क्यूरीज न्यू आएंगी हमें चैटबॉट को ट्रेन करवाने के लिए फिर डेली मॉडल ट्रेन होगा आंसर देने के लिए.
You're right. Model will be trained. See here, I mean, this is actually this concept. मेरे ख्याल में मैं अभी इसको मेरी जो डीप लर्निंग की क्लास है उसके लिए मैं तैयारी कर रहा था. It's actually a model like I don't think it is here. Yes, this one. See here, this is encoder, this is the sequence, and this is its corresponding sequence. Right. So everything here is RNN. This is RNN. This is RNN. So all these encoders are RNN. All these decoders are RNN. So usually you use RNN or LSTM or GRU in sequence to sequence translation. You can see here it follows a typical encoder decoder architecture where both encoder and decoders are generally variants of RNN, such as LSTM or GRU. So everything here is either LSTM, GRU, or a simple RNN. And they are doing nothing. They are just mapping these sequences on these sequences. So we say when this is the sequence, li, peti, the answer should be the little bird took its flight. Right. This is translation. This is translation from, I believe, French to English. But there can be another translation. The another translation is, what is deadline of applying OGDC and DHP? The answer should be the application deadline for OGDC and DHP is September 10, because this is again a sequence to sequence problem. And chatbot, the first sequence is the query and the second sequence is answer of that query. So if you are able to create all these queries and then train your encoder decoder on those queries and answers, then your model should be answering those queries which you may not have input at the time of training the model, because that is machine learning. So it will automatically learn what next character should I be predicting. Believe me, here each of these RNN is actually predicting this word. So this RNN says, from the encoder training, I understand that when I see start, I should produce the. When I see the, I should produce little. When I see little, I should produce bird. Because when you want to predict took, TOKK, at that time you have already seen the little bird. So when you want to predict here the next word at the time 3, then you have already seen these 3 words. The little bird took. Right. Now when you already have seen this combination, the little bird took, then the next word which should be predicted is its. Right. And when you have already seen the little bird took its, then the next word predicted should be flight, and so on. Right. So when you are training your model on a different sequence, a sequence to sequence model can do machine neural translation, it can do chatbot, it can even map one DNA on another DNA, it can generate text, it can write a script for new drama, it can sequence to sequence. Your music is a sequence, so it can even generate a new tune for you. It can do the things that A.R. Rahman have been doing, in Bollywood, right? So the thing is, if you can train your model properly, it can generate a new sequence, or it can answer a query on which it has been trained in past. Right. So let us understand the basics of RNN. I think enough motivation why RNN is important. Now let us see how to work with RNN and what actually RNN is. So in today's class, first we will see the RNN mathematics and then we'll try to implement it. Right. Okay. So all these hidden states, I mean, they usually say you can roll them in and they are recurring state. Uh, we can call them just one hidden layer, but that hidden layer can be unleashed. It can have as many states as you want. It actually depends on how big your sentence is, how big your dependency in the language is. If that dependency is too long, if your sentences are too long, then you can have maybe even 100 these recurring neuron. But if you say that dependency is very short, then you can have 2 to 3 these recurring neurons. But the thing is, these recurring neurons will be able to get input from the sequence, right? So these are just 3 equations you need to understand. When we were working with the dense neural network, we saw what is Y. There we saw, if you can recall, Y equal to X WT plus B, where these are weights. This is your input, and these are biases. These are bias. So your Y actually had this value. Now, if you closely observe, Y is only dependent on X, nothing else. Y is only dependent on X, right? The current input. Obviously, weights and biases you are generating, but Y is only dependent on what current you are providing it. So when you are talking about sequential neural network, you provide one word at a time. So this X initially might be what, then it might be is, then it might be lost, then it might be date, and so on. So one word at a time, right? But when you see a recurrent neural network says Y equal to weight matrix and HT, certainly. Huh? Now what is HT? The actual magic is in HT. Now HT we call current state. This current state is actually function of previous state and current input. Huh? The current state is function of previous state and current input. So current input is coming from here and previous state is coming from here at the recurrent neural network. And this previous state can be any number, maybe 5, 6, whatever you want. Now the good thing is, if you say that my current state is function of previous state and current input, then this previous state means that it must have seen previous input and the input before that, right? So it actually becomes a cascading phenomenon where when you are processing current input, you are actually seeing what happened in past, and that past is being represented by previous state, right? And that function can be any function, any activation function. It can be 10H, it can be sigmoid, it can be softmax. I mean, whatever activation function you want to apply, you can do that, right? But some non-linear function, right? Because neural network is all about non-linearity. If you can only sum them or linearly subtract them, then it won't be doing good learning. So for encouraging learning, we will do any non-linear activation function. So here, the activation function that we usually use at middle layer is 10H. Yes?
Sir, there must be some initial state जहाँ से हम start लेंगे, तो वो हमारे पास यहाँ पे जो first function है उसमें, क्योंकि जो हमारे पास current state है वो previous state की base पे base कर रही है. तो फर्स्ट इनिशियल स्टेट हमारे पास क्या होगी?
Very good question. Very good question. And Noor, you will get answer of this question when we'll be doing mathematics for that. Just 2 minutes and you will see the answer, right? So we do an activation. Now see here, what is your HT minus 1? I mean, what you saw previously, the input that is coming from here. So what you saw previously, it's actually nothing. It's the previous input multiplied by a weight matrix, and that weight matrix for hidden layer. That weight matrix for hidden layer, right? And you know that these weight matrices initially they get random value, and as you train the network, these weights are updated, right? And then we are adding, you know, current input and weight matrix for the input layer. This is weight matrix for input layer, and this is weight matrix for hidden layer. So you need to understand that when X is coming to the network, this will be multiplied with a weight matrix, initially random value, and as you do back propagation, these random values will be updated. And then the hidden layer, it is getting H from here, it is getting input from here, but that input will also be multiplied with the weight matrix, and that weight matrix is another random weight matrix. We say it is weight matrix for hidden layer, right? So we do calculate this quantity, then calculate this quantity, add both of them, perform non-linear activation, that will give you H3. And next time when you see next input, this HT becomes HT minus 1. And as Noor asked, okay, so when you are at time stamp 3, then the previous state is 2. When you are at time stamp 2, the previous state is 1. And when you are at time stamp 1, the previous state is 0. 0 means you saw nothing. So at that time, your input vector will be all zeros. We'll see that when you see mathematics. Huh? So you calculate current state, which is actually this one, and that current state with another matrix, I mean a random weight matrix, which is for the output. When these two are multiplied, you get output. You get output, right? So output previously, I mean in our fully connected y equal wx plus b, b is usually constant, so we can ignore it. So y was w into x, where x was input. But here y is not dependent on input. It is dependent on current state, and current state is actually previous state and current input. It means that now we are not only considering current input, but we are also considering what we saw previously. Wow, what a beautiful concept, right? In fully connected, we just depend on current input, y equal w into x. But here we are not dependent on only current input, we are dependent on HT. And what is HT? HT is actually function of previous state and current input. So that is the reason why your RNN is able to capture the context. I mean, that is the reason why RNN will be able to understand what I saw before P. Huh? Or maybe what I saw, you know, when I say what should be next word after drink. When you are doing fully connected dense neural network, you will only be, the only accessible thing will be drink. But now because it is RNN, so you say the previous state is true. Now this true is actually encoding not only true but also loves, right? Now this loves is not only encoding loves, it is also encoding she. So in a way, when you are passing drink and when you pass true, true is actually hiding in itself whole the information it has seen previously. So you know that when you say previous state, it does not mean only previous state. It means that full history in past. What was before true, what was before love, what was before she, and so on. So you can see that this RNN is actually an excellent mechanism of capturing the previous context, just with simple idea. Just with these 2-3 simple calculations, you are able to develop all these modern tools like chatbot, like machine neural translation, and so on, right? Let's see the mathematics behind it. Noor, you will get answer now that what will be input when we are at time stamp 1. So they say that this is, you know, your input neuron, your output, you will have hidden layer, right? Usually we apply softmax at the output layer, we apply ReLU or 10H at the hidden layer. If you unfold it, you can see input and output, and here you can have other activations, right? And then usually this W3, W2, you know, because all of them get same weight matrix, so they can be called W. You should not call them W2, W3, W4 and so on, because they are usually getting same weight matrix. These weight matrices are same. So that is the reason why we call them recurrent neuron. These are all same neuron. They might have different values, but their weight matrix is same. So that is the reason why we can write them here W, W, or B and B. You can see we have removed the subscript. The reason is their weight matrices are same. So that is the reason why these hidden layers are actually known as recurrent neuron, right? And you can simply show them because they are recurrent neuron. You can have this arrow and then, you know, the neuron. Let's see this example. HT and HT and YT, you've already understood. Let's say we want to process hello. We want to process hello, right? Now, Anas, how many unique words are there in hello? Anas, how many unique words are there in hello?
These are
Sir, three.
the characters.
Yeah,
The characters.
unique characters. How many unique characters are there?
Sir, 3 unique characters.
Okay, three.
Unique.
Three. Are you sure?
No, sir.
Come on.
Four, sir. Four.
Four. Right. There are four.
Yes, sir, 4.
There are 4 unique.
Sorry, sir.
Okay. H, then E, then L, and then O. Right. Okay. Now, when there are 4 unique characters, what should be size of each character in 1 hot encoding? Murtada? Murtada?
Yes, sir.
What should be size of each character in 1 hot encoding? Shadib?
4.
Shadib? Shadib?
Shazib.
It has to be 4, right?
4, sir.
Yeah, this is H, and in 1 hot encoding,
0, 1, 0, 0.
this is E, right? And in 1 hot encoding, you know,
0, 0.
This is L, right? And in 1 hot encoding, you know that this is O, right? So in 1 hot encoding, you know, when you vectorize hello with 1 hot encoding, this becomes H, and this becomes E, and this becomes L, and you know, this becomes O, right? Okay, so in 1 hot encoding, you can see H is this, E is this, L is this, and O is L is this, right? Now, say for example,
सर यहाँ पे O नहीं आना चाहिए.
You're right, but you know, here I want to predict what should come after H, E, L, L. What should be the prediction? So when I give these 4 characters to my model, what should be the next prediction? Right. So we'll give 1 character at a time and then ask model, tell us, you have seen 4 characters, tell us what should be the 5th character. Right. So these are our inputs, H, E, L, L. And we want model to predict the next character, which should be O. And let's see what model actually predicts. Okay. So, guys, let's take a break of 10 minutes because I do not want to lose. Today, actually, my machine's battery is not working. So, if power fails, then this recording.
Sir, 10 मिनट के बाद नमाज की ब्रेक करते हैं ना? 1:25 पे नमाज होती है.
1:25 पे नमाज होती है.
ओके, आप 1:15 पे ब्रेक करते हैं. 1:15 पे 1:10.
ठीक है. असल में मैं ये नहीं चाहता कि यहाँ पर ना कोई पावर का झटका आए और ये सारे रिकॉर्डिंग लूज हो जाए ना. असल में मेरी इसकी बैटरी आज खराब हो गई है. सुबह से 1-2 झटके आए हैं लाइट के, तो I don't want to lose the recording. That is the reason why.
अभी कर दें ब्रेक है सर, वो नमाज की
सर बेशक बात सर फिर अभी कर दें।
1:15 करते हैं, 1:15 करते हैं, ठीक है ना?
चलो सर ठीक है सर।
ओके, 1:15 से
फिर हम रिकनेक्ट हो जाते हैं ना।
1:15 से 1:35 पे करते हैं, ठीक है?
यस सर, यस
ठीक है सर, ठीक है।
Okay, so here now let us process it. So we know that ht is equal to function of previous state and current input. Previous state is actually this quantity, the weight matrix for the hidden layer and previous state, and weight, and then this x3 is actually weight matrix for input layer and current input. So say for example we are passing h. Now this is network, so we are now initially passing h. Now for wxh, say for example we have generated these random values. We have generated these random values. Nothing, just these random values by wxh. So this is our wxh. You know that generating a random matrix of 3 by 4 is not a big deal. We have already done it many times in Python. So we are generating wxh, which will actually help us in estimating this quantity, which is actually dot product of input and this one. Right. Now, what is the first input? The first input is h. It means that input will be 1 0 0 0. Right. So let us calculate wxh into x3, which will be actually dot product between this matrix and this matrix. Right. So dot products between these two matrices. So you can see wxh into this. Right. When we apply dot product, we actually multiply this with this plus this with this plus this with this plus this with this. You know that this actually becomes 0.28 plus 0 plus 0 plus 0. So the first element is 0.28. Then we, this is broadcasting. I mean, this is Python. This is TensorFlow. I mean, had it been in typical calculus matrices, then it would have raised objection. It would have said these are two dimension of the networks which are compatible for matrix multiplication. But we say in TensorFlow we do broadcasting, right? So this first row is multiplied with this whole column, we get this value. Then second row multiply by same column, we get this value, because 0.90 into 1 plus 0.87 into 0 plus 0.69 into 0 plus 0.18 into 0. So we get output 0.90, and then 0.53 into 1 plus 0.09 into 0 plus 0.55 into 0 plus 0.49 into 0. So we actually get 0.53. Right. So we have done this quantity. We have calculated this quantity. Right. The next thing that we want to calculate is actually this quantity. It means that we need a random vector and the previous state. Now here we do not know the previous state. The previous state is actually all 0. Right. When you are at time stamp 1, the previous state will be 0 0 0 0. Right. It means that all 0, because we have not seen anything. But when you are at time stamp 1, the previous state is all zeros. Right. It means that we will be multiplying our hidden layer matrix with all zeros when we are at time stamp 1, when we are providing input h. So when you provided input h, the previous input is all zeros. So here, say for example, this is my hidden layer matrix. It is still matrix, one value, but it is still a matrix. And say for example, the biases for that layer is actually this value. Right. Now, WHH plus bias into previous input, which is all 0. Right. Now, you know that you actually multiply this value with this, right, and then plus this thing. It will be equal to 0.56, 0.56 and 0.56, right? Because WHH into H minus 1 plus bias, you know that even in this quantity, we are not showing bias because it is constant, so we are not showing, but actually we are adding the bias. So in this case, my bias value is equal to 0.56. So the formula, you know, for our neural expression is weight into input plus bias. So weight is actually this 0.42 n to input. Input is all 0, which means that this quantity will be 0. This quantity will be 0. So these will be all zeros, and then we add bias in it. So bias is 0.56. So again broadcasting 0.56 plus 0, 0.56, 0.56 plus 0, 0.56, 0.56 plus 0, 0.56. So output here is 0.56, 0.56 and 0.56. It means that the first quantity is this, and you know this quantity and this quantity. So this is the first quantity, which is actually this value, and the second quantity, which is this one, is actually this value. Right. So the next step is, when you see here, we add both of these quantities and apply 10H. So let's do that. Let's do that. Right. So we this quantity plus this quantity is equal to this one, and on this value we are applying 10H. When you apply 10H on this, the result is this one. Right. So 10H for 0.85 is 0.69. 10H for 1.46 is equal to 0.89, and 10H for 1.10 is 0.80. And remember, 10H is actually this one. 10H is actually e power x minus e power minus x divided by e power minus x plus e power x. Or alternatively, it is actually equal to 1 over e power minus x plus 1. Right. So you can see, let's do one calculation. Let's do just one calculation. So if I do open, say for example, Excel, okay, say maybe I can write here equal, my three values are, 0.6931. Okay, 0.6931, 0.6931. Okay, okay, so this is my first value. So I say equal to exponent this value. Right. So I actually get e power this value. I get e power this value. The formula is actually e power minus x. So I can say e power minus this. Right. So I get this value, and you can see it is 1 over e power this value plus 1, which is equal to 1 over this. Right. 1 over 1 over this and plus 1. Right. So this becomes 0.66. So this becomes 0.66. So you can see where is that? Where is that? 10H point. Okay. Where? Yes, it is this one. Almost same value, 0.66. This is 0.69, but we got 0.66. Maybe some of the fractions I'm missing. So the answer, so the overall, the calculation for this one is, we add both of these quantities, right, and then apply 10H. So 10H on this, 10H on this, and 10H on this. You will get these values, right? And you know, this is the simple formula for 10H, right? Okay, so now when we gave H, we actually calculated the HT. Now, when we give E as input, you know that now we have got previous state. What is previous state? This becomes the previous state. This becomes the previous state. Right. Now let us give E as input. Now when you give E as input, right, so first we calculate this quantity and then we calculate this quantity. So WHH and HT minus 1. What is HT minus 1? The previous output. The HT which we had at this stage, so 0.69, 0.89, 0.80. So you can see previously we were using HT minus 1 all zeros, but when we give E, we actually give HT minus 1, which is equal to the one we calculated when we gave H. So which is 0.69, 0.89, and 0.80. Right. So this is HT minus 1 here. When we give E, WHH is actually same. We have calculated, and then plus the bias value. Right. So this is actually added in this, and we get this quantity. So WHH and HT minus 1 equal to 0.86, 0.95, 0.90 when we give E. Right. Now let us calculate WXH and X3 when we are giving E. So this is your E, this is your WXH. So their multiplication gives us this value. Right. So we can add both of these quantities, apply 10H. So the output is actually this one. So when we give E, this is the H3. This is H3. Right. Now at this stage, when we have already given H and E, let us see what is YT. Let's see what is the output. Right. So output is equal to another weight matrix at the output layer into H3. So when we gave E, this is our H3. We calculate YT here. Right. So YT equal to HT, which we have calculated, and this is another random weight matrix. So we generate this one into HT and we get this YT. At the output layer, we apply softmax, right? So we apply softmax on these values. We apply softmax on these values and we get this probability. We get this probability. Now is the most important point. You need to be able to interpret it. If you interpret it, you know which character has the highest probability? Which character has the highest probability?
H, sir, H.
H, for H. Huh? Because we have got 4 unique characters. The first is H, second is E, third is L, fourth is O. When we gave H and E, the model gave us the highest probability for character H, which means that model predicts that after H and E, the next character should be H. You might argue that, come on, this is wrong prediction. You know that it is wrong prediction because we have trained model only on 2 characters. Right. Now, Sarwan, what we should do when the prediction is wrong?
Sir, again, we have to train the model.
How? What we do? I mean, when we calculate error, then what is the next step?
उसकी वैल्यू अपडेट करेंगे WH की.
Sir,
how to update the value?
सर लॉस फंक्शन को यूज करके हम वेट चेंज करके फिर यूज करेंगे.
Exactly. We use loss function. We see error value. We do back propagation. The back propagation, the way we have been doing in our fully connected dense neural network. We have our error function, which is actually predicted value log actual value, and we do this sum for all the outputs, for all the outputs, and this output is dependent on this and this value, right? This output is dependent on this and this value, so you will actually update all these values, and you know how back propagation works. It's a chain rule, right? So when you do this back propagation, next time when you again give H and E, it may not be able to predict L, but something very close to L, right? So the probabilities will be updated. That's all. That's all, right? So each time the cross entropy error is first computed using current output and the actual output. Remember, the network is unrolled for all the time step. For the unrolled network, the gradient is calculated for each time step with respect to the weight parameter. Now that the weight is same for all the time steps, the gradient can be combined together for all time steps. The weights are then updated for both recurrent neuron and also for the input and output neuron. And when that happens, the next prediction will be much improved. It will be closer. I mean, your error value will be reduced. The most important thing is, I mean, you need to understand when you gave H, the input is all zeros because at that time there is no previous input. So all the inputs are 0. When you gave E, when you gave E, at that time your HT minus 1 is already available, and you calculated HT minus 1 when you gave H. So that is your HT minus 1 in next time stamp. It is HT here in current time stamp, but when you are in next time stamp, this becomes HT minus 1. This becomes HT minus 1. And you need to understand mathematically, when you are giving, say for example, when you are, if this is one big sentence, ELEPHA, right? Now, I want to say what should be the next character. You say the previous state is A, but with previous state A, H is being represented. Now, because in A, H is being represented, in H, P is being represented, in P, E is being represented, which means that when you gave A, you did not give only information about H, but you actually given information for all these characters, because H is embedding P, P is embedding E, E is embedding L is embedding E, and so on. So that is the reason why your RNN is very smart. You just give him one previous state. That previous state is actually have already captured the previous state, and that previous state has already captured previous state. So it means that when you are giving just one previous state, you are actually capturing whole context which model has seen so far. And when that happens, the predictions become very accurate. I mean, the only thing you need to make sense of it is this difference. It is actually this difference. We say that in fully connected y equal to w plus x, whereas in RNN y equal to, there has to be some function. There has to be, some function on this. There has to be some function on this. Here in RNN, some function on W, you can call maybe hidden state WH, right? Into HT minus 1, right? And WX, maybe I can call hidden layer current input. So present WP, WP into WP into current input, which is X, right? That's all. This is the only difference, right? So here you can see only one quantity, but here two quantities. The one quantity is representing what happened in past, and one quantity which is telling you what is present. So Y in RNN is not only about what you see now, but it is also about what you have seen in past. That is the reason why it is able to do prediction much better than a fully connected dense neural network. Right. So I hope.
Sir,
yes.
Sir, break करते हैं.
Okay, so we are going to break here. मैं यहाँ से स्टॉप भी कर लूंगा ताकि ये रिकॉर्डिंग सेव हो जाए और मैं दोबारा 1:35 में ना कनेक्ट हो जाऊंगा. ठीक है?
Okay, sir.
Thank you. 15 minutes break. Come back in 15 minutes.
Okay, sir.